Sergey graduated in Stanford. Um, he's currently a professor at UC Berkeley. Um, his work focuses on machine learning for decision making and control, mostly deep learning and reinforcement learning as applied to autonomous robots. Sergey, please.
All right. Thank you, Roy, for the introduction. Sorry about the little AV mishap. All right. So since this is the first talk of the day, I'm going to talk about control as inference, and I'll actually talk about some of the basic kind of theoretical underpinnings of control as inference and a particular framework that I'm pretty excited about. And I'll also talk about some of the new things in our own research in my group. But to start with a little bit of motivation. So as many of you probably already know, with the recent developments in machine learning, we're actually pretty good at building machines that can learn to perceive, meaning that we can build machines that can learn to recognize objects and images. For example, in large diverse data sets like ImageNet, we can build really good machine translation systems, really excellent systems for recognizing speech, and so on. So then the next question we might ask is, well, what about machines that can learn behaviors? What are some of the challenges that come up there, and what can state-of-the-art machine learning techniques do to make this possible? To make it possible, for example, for autonomous cars to learn how to drive, for drones to learn how to fly around, for robots to learn to do chores in your house or save you from a disaster. Well, the basic idea, and the one that we actually study quite a lot in my group, is that we can develop these kinds of methods by combining high-capacity representations, which are deep neural networks, representations that can generalize effectively, with algorithms that provide us with a mathematical formalism for decision-making. And these are reinforcement learning algorithms. So reinforcement learning algorithms essentially tell us how we can train a model in order to make decisions, and deep networks tell us how we can construct representations that are capable of actually generalizing effectively to complicated open-world problems. So that's kind of the idea, and it sounds very appealing. And of course, we've seen quite a few successes in deep reinforcement learning over the course of the last few years. We've seen deep reinforcement learning algorithms that can play video games, play really complicated board games, beat world champions like Go, and so on. But something we haven't seen quite as much of is deep reinforcement learning algorithms that actually learn directly from real-world experience on real-world physical systems. And we might ask, well, why is this the case? What are the big challenges that are preventing robots being all over the place in the world around us, learning through reinforcement learning? And I think there are two really big challenges that I want to focus on today, and some of these you guys might all be quite familiar with. The first one, of course, is that deep reinforcement learning algorithms tend to require quite a large amount of data in order to learn complex skills. So in this video, for example, you're seeing the humanoid running task. It's a very interesting task. It's really quite awesome that we can have deep RL algorithms that can learn this task, but in order for a deep RL algorithm to even begin making progress on a task like this, you need the equivalent of about 10 hours of real time. So of course, this is a simulated task, but if this was a real robot running around, it would need to run around for 10 hours before it even begins making progress, and then maybe another 50, 60 hours after that before it converges, which is of course quite expensive to do in the real world. The other challenge, which is perhaps a little more subtle, but that practitioners of deep reinforcement learning will be very familiar with, is that deep RL algorithms tend to be a little bit unpredictable and a little bit unstable. So this is an even simpler task. This is the so-called half-cheetah task, and this is a plot borrowed from a paper by Islam et al. In 2017, showing two curves that are constructed by averaging together 5 runs from RL algorithms, except that these are 5 runs from the same algorithm for each one. So one group of 5 ended up way better than the other. And this is actually because this task has a couple local optima that have drastically different performance. And this is very typical in deep reinforcement learning. So in this talk, I'm going to discuss how recasting optimal control and reinforcement learning as probabilistic inference can actually help us take steps towards addressing these challenges. So I'm going to start off with a bit of theory and a bit of a conceptual framework that recasts reinforcement learning as probabilistic inference and introduces this notion of soft optimality or maximum entropy reinforcement learning. And then I'll tie this back to the challenges that I alluded to and discuss some practical deep RL algorithms based on this connection that actually take some steps towards addressing those shortcomings. And then I'll conclude with a discussion of some applications. I'll talk about some applications in robotics, some applications for learning compositional policies, and also hierarchical reinforcement learning. But let's begin with the algorithmic framework. When we started working on this, and I should say, by the way, that a lot of the work I'm going to discuss was led by a PhD student named Thomas Harnoya, who's actually graduating this semester and is on the job market. When we started working on this question, we actually had a very particular, very specific challenge in mind. We thought, well, okay, you have this little running humanoid, you can train a policy for it, but if you run basically the same algorithm twice for this little running humanoid, you'll get two different policies. They're both actually successful, but they look very, very different. So we thought, okay, well, what's going on here? Can we construct some sort of like simple little toy task that captures the essence of this challenge? And here's one example that we thought of. Let's say that you have this little quadrupedal robot. Now it's simpler, it's lower dimensional, and it lives in a little maze where its goal is to reach this blue square. Now, when it begins exploring, it can make progress either along the upper passage or along the lower passage. Initially, both passages look promising because both bring it closer to the goal. So it gets a little bit of reward every time it gets closer to the goal, and a big reward when it actually reaches the goal. So initially, both look promising. And if it accidentally makes it a little bit further along the upper passage, it'll reinforce that behavior, probably abandoning the other one, and commit all of its probability mass to exploring the upper passage, which of course will lead to a local optimum. So the ideal strategy for a problem like this is to explore both hypotheses about equally until you figure out which one is more promising. So we thought for a minute, well, how can we design RL algorithms that can actually do this? So before I explain the intuition for the solution that we came up with, I want to provide a short primer on Q functions and reinforcement learning. Many of you might already be familiar with this, but I want to make sure we all get on the same page. So of course, in reinforcement learning, we have an agent that interacts with the world. The agent chooses actions A, and the world responds with a state that results from that action S, and a reward function R of S comma A. The agent chooses actions according to an action distribution pi, which is a conditional distribution A given S, so we refer to that as a policy. And the objective in reinforcement learning is to maximize the expected total reward under the policy pi. That's basically the RL objective. And I want to point this out because we will see other RL objectives later when we combine reinforcement learning and inference. Now, one very useful object in reinforcement learning is what's called the Q function. The Q function is a function of the state and the action, and the Q function goes with a policy. So when you see me write Q pi, that's the Q function that goes with the policy pi. And it tells you if you start in state S, then take action A, and then follow the policy pi, what is the total expected reward you will accumulate? And the nice thing about Q functions is that if you can calculate the Q function for a policy pi, you can construct a new policy that takes an action with probability 1 if it is the argmax of Q, and you can actually show that such a policy will be as good or better than the old policy. So that naturally leads to a procedure for improving policies. One way you could do it is you could fit Q functions and update policies, and that's a policy iteration procedure. You could also actually try to calculate the Q function for the optimal policy directly. If you do a little bit of math, you can show that the Q function for the optimal policy must satisfy the Bellman equation. So I'm going to use Q star to denote the optimal Q function, and it has to satisfy the equation Q star is equal to R plus the max over the actions of the next Q. So if you can find a Q function that satisfies this, you know that it will correspond to the optimal policy. So one way that you can learn an optimal policy is you can enforce this equation at all the states. Basically, take the left-hand side, subtract the right-hand side, square that, and just minimize that error everywhere. And then you can also find the optimal policy. And this is the essence of Q learning. Okay, so that's a very short primer on RL. But now let's bring it back to our maze problem from before. So if we visualize the Q function at the initial state for this robot, the way that I'm visualizing this is the x-axis is sort of a 1D projection of the action, and the left peak corresponds to going left, and the right peak corresponds to going right. And this is, imagine this is in the early stages of training where this guy made it a little bit further along the upper passage than along the lower passage. So these are not the correct Q values, these are just the ones that he's estimating. So to him right now, the upper passage looks a little bit better. So if you take the policy to be the one that maximizes the Q value, maybe it'll be very heavily centered on that left peak because it's just a little bit taller, and the robot will exclusively explore the upper passage and forget about the lower one. So perhaps what we'd really like to do is we would like to commit our probability mass somehow in proportion to some positive transformation of the Q values. You can't commit probability mass directly in proportion to Q values because they might be negative, so we have to somehow make them positive. But then you can explore both peaks depending on how large their Q values are. So it turns out that an exponential transform has some very favorable theoretical properties, so we'll do that. We'll explore the peaks in proportion to the exponential of their Q values. The robot will still go in the upper passage a bit more often, but it will keep exploring the lower passage, and hopefully it'll make gradual progress along both until it figures out that the lower one is better. So if you want your policy to be proportional to the exponential of the Q function, one of the ways that you can do this is you can optimize the following objective. You can minimize the KL divergence between pi and a distribution that's proportional to exponential Q. So there's a normalization factor, that, of course, there that's missing. But if we write out the definition of the KL divergence, then up to an additive constant, it's equal to the expectation under pi of q minus log pi. So that's just the definition of KL divergence, modulo a constant. So if you look at this equation, you'll see that actually the first term simply gives you the expectation of the reward, and the second term is just the entropy of pi. So we've recovered something that looks an awful lot like that original reinforcement learning objective, only now it has this entropy term in there. So we call this the maximum entropy objective. And if we optimize this objective, we'll actually get this guy to explore both the upper and lower passage. The intuition behind this is actually quite interesting. We're saying, try to be as random as possible while also maximizing reward. So it kind of makes sense that if you want to be as random as possible while maximizing reward, you look for all the different ways that you can maximize reward, including both the upper and lower passage, until one of them looks clearly better than the other. But it turns out that actually there's something a lot deeper about this objective. It turns out that you can actually use it to draw a very interesting connection between reinforcement learning and probabilistic inference in graphical models. So here's how we can do this. In optimal control, we ask the question, which actions lead to optimal futures? Which actions will maximize reward? In control as inference, we ask the question, which action was taken given that you are optimal in the future? It sounds a little bit funny, but it's actually an inference problem. It has evidence. The evidence is that you were optimal in the future, and there's a variable that you're asking a question about, which is your action. That's your query. So we can draw a graphical model in which this inference problem can be performed. We start off with a graphical model for an MDP, so it has states and actions. And then we add variables that denote optimality. This is a little bit weird, but these variables are going to be binary variables, and the probability of these variables being true, given the state and action, is equal to the exponential of the reward. You have to assume the reward is always negative, but you can assume this without loss of generality because you can always subtract or add a constant. Okay, so it's a little bit of a funny graphical model, but that's the graphical model we're going to go with. And our evidence will be that OT is true at all time steps. That's our evidence. And now we're going to want to infer the probability of the action given the state and given that all of these OTs are true. And that'll be our policy. And we can actually show that for a particular variational inference procedure, this policy maximizes the maximum entropy reinforcement learning objective. So let me just write out the distribution that's implied by this graphical model. It's kind of a lot of math, but it's basically just a product of, over time, of three different kinds of CPDs. First, there's the initial state distribution P of S0, and then at every time step, you take the product of the probability of OT, which is the exponential of R, and the probability of the transition, P of ST plus 1, given ST-AT. And now what we're going to do is we're going to do structured variational inference in this model, so we have to construct a variational distribution, and we're going to construct kind of a weird variational distribution. Here's what that distribution is going to look like. We're going to actually set the variational distribution, which is Q over all the states and actions, to contain the same CPDs as the original distribution for the initial state and for the dynamics. So Q will actually be equal to P of S0, that's not a typo, it's actually P, not Q, times the product over time of P of ST plus 1 given ST-AT and the policy pi of AT given ST. So the only thing in the variational distribution that differs from the original is the pi. That's the only thing you're changing. So when you do variational inference and you refit the variational distribution, you're only going to be changing pi. You will not change P of S0 or the dynamics. And that's very important because that's what lets us recover the maximum entropy RL objective. So the graphical model corresponding to the variational distribution looks like this. So you can see the original one doesn't have an edge from S to A. The variational one has an edge from S to A, which represents the policy. So now we're going to do a little bit of algebra, and this is probably the most math-heavy slide in this talk. The variational lower bound is given by the expectation under Q of log Q minus log P. So if you write that out, you get a big wall of math, but it turns out that almost all the terms here cancel. So I just substitute in the equation for P and the equation for Q, and of course, because of how I chose Q, the initial state distributions cancel. Those appear on both the left and right side. The dynamics cancel, and all I'm left with is a sum over log pi terms and a sum over R terms. So that means that the variational lower bound is simply the negative of the expectation of the reward plus the entropy, which is the negative of my maximum entropy RL objective that I showed before. I wish I could say I came up with this, but of course, this idea, this connection between control as inference is decades old, and I'll show a long list of related work later. Okay, so that's kind of neat. We can do variational inference, and it corresponds to maximizing a maximum entropy version of the RL objective. But how do we actually optimize this objective? Well, we have a few choices. So one choice is we can use standard on-policy policy gradient algorithms. So we can actually take this original objective, differentiate it using the likelihood ratio policy gradient estimator. It turns out to be very easy to do. You just subtract log pi from your reward, and you can actually optimize it with any standard policy gradient algorithm. In fact, policy gradient methods have been using this trick without necessarily connecting it to variational inference for 2 decades at this point. But there's another option that's also quite interesting that allows you to build off-policy algorithms, which is to modify Q-learning in order to optimize this objective. And this is, again, something I didn't come up with. I actually read about this in Brian Zebart's PhD thesis, but I'm sure it's been around actually even longer than that. So in standard Q-learning, as I mentioned before, you'd like your Q values to be equal to the reward plus the max over the next action of the Q value. It turns out that if instead you modify Q-learning to do what we call soft Q-learning, you can actually optimize the maximum entropy objective. So the only change here is that instead of the max, you replace that with a log of an integral of the exponentials of the Qs, which sounds a little bit arbitrary, but I'll give you some intuition for why it makes sense in a moment. But intuitively, what this equation is actually doing is the kind of soft max. Imagine if all the Qs were really big, that log of the sum of the exponentials would actually be not dominated by the largest Q. So it's a kind of soft max. For large Qs, it acts like a max. For small Qs, it kind of smooths them out. And another way that you can write this equation is you can say that the Q value is equal to R plus the expectation of the next value, where the value is given by the log of the integral of the exponential of Q. And written out like this, V looks an awful lot like a normalization constant, right? It's simply the log of the integral of xq. So if xq is your unnormalized probability, V is the constant that normalizes it. And that means that if you want to write out the policy pi of a given s and you want it to be proportional to the exponential of q, that means it's actually equal to the exponential of q minus v, which is pretty cool. Now your policy is simply the exponential of the advantage. That seems quite reasonable. And of course, that gives you this behavior where we have multiple possible good hypotheses. You'll actually explore both of them. And there's actually a pretty deep connection also between this and message passing methods. So if you imagine a message passing algorithm of the kind that you might implement in a hidden Markov model. In a hidden Markov model, you would have a backward message, and the backward message is the probability of the evidence now and in the future given the current state. So here the evidence is O, so the backward message would be P of O little t through capital T given STAT. And if you write out the equations for backward message passing, basically exactly the same as you would do in an HMM, it turns out that the logarithms of those messages correspond to the Q function and the V function. So the logarithm of the state action backward message is the Q function, the logarithm of the state backward message is the value function. So that's actually pretty neat. That means that dynamic programming implements message passing in this model. And of course, the A given S is given by the ratio of those messages, which of course means that pi is equal to the exponential of Q minus V. So that's kind of neat. Essentially, Q learning and message passing are doing kind of the same thing. Okay, so this is the maximum entropy objective that I introduced. It basically solves the inference problem of trying to find P of A given S, comma, O at all time steps. And there have been quite a few algorithms in recent years that either implicitly or explicitly optimize this objective, including some older work listed at the bottom, some newer work listed at the top. And I'm going to talk about, in the next section of this talk, about the first two, soft Q learning and soft actor critic, which were developed at UC Berkeley in my group. All right, but first, a little bit of related work. As you can see, the first reference there is from 1960, so this idea has been around for a really long time. If you're interested in some of the history behind the connection between control as inference, I encourage you to check this out. Another quick side note, if there are any Bayesian people in the room, people that are inclined to think about uncertainty in reinforcement learning, one thing I would say, this is not Bayesian reinforcement learning. There is such a thing as Bayesian RL. People have asked me this. That's not the same as this. This is RL with Bayes nets. You can also make it Bayesian. You can introduce uncertainty, but that's not in there by default. Okay, so let's talk about some practical algorithms that build on this framework. So I'm going to talk about two algorithms. The first is soft Q learning. Soft Q learning is an algorithm that builds the optimal Q function for the maximum entropy reinforcement learning objective directly, which turns out to be fairly simple to do. The trouble then is actually choosing actions according to that Q function, because choosing actions requires sampling from the exponential Q distribution, which for continuous actions is of course intractable. So we have to employ some approximate inference procedures just to sample from that. But the learning ends up being a bit simpler. The second algorithm is called soft actor critic, and soft actor critic learns the Q function for a given policy and pi directly. And this corresponds most closely to variational inference because pi, of course, is part of your variational distribution. It turns out to be a little more involved, but substantially more stable and scalable in practice. So let me talk about soft Q learning first. Soft Q learning has a very similar structure to other kinds of Q learning algorithms, like DQN, for example. The main difference in soft Q learning compared to regular Q learning is simply that we use a softmax instead of a hardmax in the Bellman backup. So it alternates between these steps. The first step is that you update your Q function. So your goal is to make the Q function at every state in action equal to the reward plus the log of the integral of the exponential Qs, which is basically the softmax. And you can actually show, as I mentioned before, that this optimizes the maximum entropy RL objective. Of course, in a practical implementation, the way that you do this is you sample a batch and you take one gradient step on that batch, just like you do in other Q learning algorithms like DQN. The second step is that you have to train a sampling distribution. We don't call this an actor-critic algorithm because the policy pi doesn't actually influence Q. It's sort of a one-directional relationship. The purpose of pi is just to sample from the exponential Q distribution, which you have to do approximately because this is difficult for all the same reasons that energy-based models are difficult. You can use a variety of methods here. Running MC online would probably be a bad idea if you're doing RL, although you could. We use something called Stein variational gradient descent, which does the job reasonably well. And then, of course, you interact with the environment and collect more data, and then repeat this all in a cycle. So structurally, the way you'd implement this is it would look very, very similar to Q learning. You just replace the hard max with a soft max, and if you're in continuous action space, also train the sampling network. So next, let me talk about soft actor critic. Soft actor critic more directly corresponds to variational inference, and the way it looks is like this. In step one, you update your Q function, this time not to find Q star, but to find Q pi. So the Q function is updated to move closer to the Q value of the current policy, just like in policy evaluation regular RL, except now you subtract log pi for the next time step to account for the entropy term. And you can show this converges to Q pi for the current policy under the maxent objective. And then you update the policy by minimizing the KL divergence between pi and the exponential Q. And again, you take only one gradient step on this objective in practice to get a nice kind of cyclical algorithm, just like other actor-critic methods. And then you interact with the world and collect more data. So the first step here corresponds to a kind of approximate message passing, and the second step corresponds to fitting the variational distribution. So this is actually a kind of implementation of variational inference. So if we actually run these methods, it turns out they actually end up doing very well, even on fairly complex tasks. So this is the RL lab humanoid task, which is actually a little bit harder than the OpenAI GIMP humanoid task. And you can see here soft actor critic actually outperforms all of the prior methods. The prior methods here are DDPG, which is an off-policy method, and PPO, which is a policy gradient method. And then soft Q learning does about as well as PPO, although soft Q learning is actually an off-policy algorithm, so it's quite nice that it does decently well there also. On a range of other tasks, we find that typically soft actor critic does extremely well. On the OpenAI GIMP humanoid task, you can see that it actually does fairly well at the task, even in less than 1 million steps. So this is very good performance for an off-policy RL algorithm, substantially better in many ways than prior methods like DDPG. But the thing that to me is actually more interesting is that soft actor critic is actually a very stable algorithm. So what you can see here is a comparison to an ablated version. Blue shows soft actor critic, red shows an ablated version where the entropy term is removed. And you can see that they both do decently well, but the individual runs of the deterministic version are much less consistent. So adding that entropy regularization actually gives you a lot more stability, which is quite nice. So if we have stable and more efficient RL algorithms, one of the things we can do is we can actually apply them to real-world scenarios like robotics tasks. So the next set of videos I'm going to show are actually tasks that were learned with soft Q learning. This is the first algorithm. And we're going to use them to learn a robotic Lego block stacking task using direct low-level torque control. So here you can see the learning progress at 0 minutes, 12 minutes, 30 minutes, and 2 hours. At 30 minutes, the robot can stack the Lego block occasionally. At 2 hours, it can actually stack it pretty consistently. What's interesting to me is not that it can stack the Lego block. We've had robots that can stack Lego blocks for quite a few years at this point. What's interesting to me is that after we've learned this policy, we can have the mischievous graduate student come in and perturb the robot, and the robot actually recovers. And the reason that the policy ends up being so robust is not because we train it for recovery, but it's actually because the maximum entropy objective causes it to try to maximize reward while maximizing entropy. So it injects noise during training, which forces the policy to be robust. And that's actually quite nice. In fact, there's a deep connection between maximum entropy reinforcement learning and something called robust control that basically explains why this kind of thing works. Another thing we can do is we can take the soft actor critic algorithms and we can apply it to a dexterous manipulation task. So these are some recent experiments by Christian Hartikainen at UC Berkeley. So we have this hand that we call the D-claw. It's a 3-finger hand. And we try to do a task which is a valve rotation task. So this is a little illustration of a person doing this task. And here's the policy learned by soft actor critic after about 2 hours of learning directly in the real world. You can see that it has a fairly elaborate finger gate as it rotates the valve, and it's quite precise at rotating it at exactly 180 degrees. And again, this is learned directly in the real world on the real hardware. Here's another experiment using soft actor critic. This was conducted at Google Brain, and this is a quadrupedal locomotion experiment. So here, this quadrupedal robot is actually learning to run directly using soft actor critic. Again, learned directly in the real world without any simulation, in this case in about 30 minutes of training. Another thing we can do with maximum entropy RL is we can actually compose policies. So in regular reinforcement learning, maybe this is something that some of you might have tried when you were just learning about RL. You thought, well, maybe if I learn a Q function for one reward, I learn a Q function for another reward, perhaps I can add them together and get a Q function for the two rewards added together. That's a mistake. You can't do that. It's not allowed. It turns out that actually for maximum entropy reinforcement learning, it's still not allowed, but you can actually bound how suboptimal the resulting Q function is. So if you learn a policy, for example, for the Sawyer robot stacking a Lego block, learn a separate policy for avoiding an obstacle, and you add together the Q functions for those policies, you will actually get a policy that avoids the obstacle and stacks the Lego block. Intuitively, the tightness of that bound depends on how much the KL divergence there is between the two policies. And then the last topic I'm going to discuss is how we can extend maximum entropy reinforcement learning to the setting of hierarchical RL. So one of the nice things about connecting reinforcement learning and probabilistic inference is that we can add other variables to the graphical model and get some interesting behavior. So what we're going to do here is we're going to take our original model, which has states S, actions A, and optimality variables O, and we'll actually train policies that themselves have latent variables. So you can imagine these policies might be represented by something like a VAE. In our case, we use normalizing flows. So the policy neural network itself has a latent variable H. So it's a distribution P of A given S comma H, and H has some uninformative prior, like a spherical Gaussian prior. If we train a policy like this, the policy will essentially use H for exploration. It will use H as a source of randomness, and because it's maximizing entropy, H will basically tell it, if you imagine the robot example from before, it might tell it which of the two passages to go to, the upper passage or the lower passage. Then what we can do is we can actually integrate out A and get a new graphical model that doesn't have A anymore, and that just has H and S and O. And now if you look at this graphical model where we've integrated out A, it looks an awful lot like the first one, except instead of actions, now we have hidden variables H. So what we can actually do at this point is we can treat that new graphical model as a new dynamical system and train a new policy that chooses H as its actions instead of A. And we can use this to build hierarchies. So the lowest level in the hierarchy is a latent variable policy that chooses A given H sampled from the prior, and the second level is actually a latent variable policy that chooses H1 given some other latent variable H2 sampled from the prior, and so on and so on. And you can build these layers of hierarchy as deep as you want, and then of course the highest one, you just choose from the prior. So it's sort of homogeneous in the sense that you can add as many layers as you want. And you can do some cool stuff with these kind of hierarchical policies. One of the things you can do is you can actually give different reward functions to different layers. For example, we can take the lowest layer and we can give it a reward function for this little quadrupedal robot that just rewards it for running fast, regardless of where it's running. So it sort of runs in all possible directions because it's maximum entropy. And because the hidden state is sort of its source of stochasticity, the hidden state ends up correlating with the direction in which the robot runs. So then you can take this lower layer and train a second layer on top of it that chooses H and train it to navigate a maze, like that cross-shaped maze on the right. So the upper layer is essentially driving the lower layer, choosing the H's for it to get it to run in the direction it wants. And you can run to different goals in this cross-shaped maze. Okay, that's it for the main portion of the talk. Just to conclude, one of the things I want to do is I want to discuss a little bit, what else is there? What are some of the other cool topics in regard to the connection between control as inference? One really important topic that I didn't get a chance to cover is that learning in this graphical model actually corresponds to inverse reinforcement learning. So I talked about inference in the graphical model. I didn't actually talk about learning. Learning is where you actually train the CPDs. If you train P of O given S comma A, that corresponds to learning the reward function. You can learn this from data. The foundational work on this was done by Brian Ziebart, and for that I highly recommend checking out his PhD thesis. We have some more recent work that looks at this question, including a paper that actually appeared in the main conference, where we use this as a way to robustify classifiers that can be used as reward functions. So if you imagine using a reward function as a classifier in RL, you might get sort of the world's worst exploitation problem. So this is a video of a task where a robot pushes an object to the red circle. If you train a classifier just in the naive way and use that classifier as a reward, the robot basically learns to fool the classifier. So you can see that in that video on the right, it's not actually pushing the green object, it's just sort of putting its fingers in front of the camera and fooling the classifier. If you instead use the framework of control as inference, it'll suggest a different way to update the classifier that robustifies it against this kind of exploitation and actually makes it push the object to the red goal successfully. Another thing we've been doing recently is exploring the connection between control as inference and imitation learning. So you can actually construct a cool method that combines model-based RL and imitation learning. You can train a probabilistic model on data from humans and then actually plan through that model by conditioning it on a goal. And this is work called deep imitative models, which will be presented in the Intelligent Transportation Systems workshop today. Okay, so at this point, I think I'm out of time, so I'm going to conclude, and I'd be happy to take any questions. And just one thing before I wrap up, I do want to emphasize that a lot of the work I covered was actually led by a student named Thomas Harnoya, who's actually one of the co-organizers of this workshop. So I just want to point that out. And the code is also available, and you can check out my tutorial for more details. Thank you very much.
Any questions?
So I can see at least 3 effects of this added entropy bonus. So there's one where you encourage exploration, one that makes it more robust, and both are good. But there's a third one, which is it may lead to a suboptimal policy. Like if you find a place where you have the same bad reward, whatever you do, you have a great entropy, so maybe you want to go there. Have you thought of a way to try maybe to decouple these effects and try to avoid this third one at least?
Yeah, that's an excellent question. So there actually has been work that tries to decompose these effects. There are quite a few papers that explore variants on this idea. For example, there are some papers that try to soften the Q function without explicitly introducing an entropy bonus by convolving with a Gaussian. There's a paper by, I believe, Ophir Natrium from Google that looks at this. We have some work that tries to dynamically adjust the temperature, the weight on the entropy term, that perhaps to some degree mitigates the last problem you mentioned. So yes, there's actually quite a bit of work on this. And one thing I might recommend is checking out some of the citations in the slides, which hopefully the organizers will post online to see some of this stuff.
Thanks. This is a really great talk, very inspiring. I just wanted to ask you a little bit about variational inference. So there are lots of methods in variational inference that we've been working on recently, where we want to convert the variational inference problem to message passing. So I just wanted to know what you think is required from variational inference community to help this research.
That's a really good question, and it's something I've been thinking about a lot. I don't have a great answer for you, unfortunately. So in my tutorial, which is referenced here on the slide, I do discuss how RL corresponds to message passing. The correspondence to variational inference is, that is a fact, that's true. The correspondence to message passing is a little approximate. There are a few bits that don't quite line up. So that discussion is a bit technical, so I would defer to my tutorial, or we can discuss it also offline. But the short answer is, it's a little tricky. Like, I don't have a single thing to tell you, and I wish I did.
Hi, nice talk, thank you. You have a condition where you assume that all time steps from now to the end are going to be optimal to learn the Q function. What about, only a subset of them being optimal?
Yeah. So that's I think a fascinating topic. So actually, the work that I showed on the previous slide, when I talked about classifiers, that actually makes use of this idea. So with the classifier, you say, oh, the optimality is only true at the last time step, or it's only true at some intermediate time step, and that's how you get a classifier instead of a full reward function. All right, thank you very much.
Listen, let's do it again.